In the vast darkness of the solar system, one planet has always seemed calm, elegant, almost peaceful. Saturn, the golden giant wrapped in luminous rings, has long been considered the most beautiful world orbiting the Sun. For centuries, astronomers believed those rings were ancient relics, unchanged since the birth of the solar system 4.5 billion years ago. Through telescopes, Saturn appeared serene, a distant monument drifting silently through space. But modern science has revealed something unsettling. The Saturn we see today may be only a temporary version of the planet. In 2004, a spacecraft named Cassini, a joint mission led by NASA, with major contributions from the European Space Agency and the Italian Space Agency, entered orbit around Saturn. For the first time in history, scientists could study the giant planet from close range. Over the next 13 years, Cassini sent back an enormous stream of data. Images of the rings in extraordinary detail, measurements of the planet's gravity and magnetic field, samples of particles drifting through the ring system. Each new observation slowly dismantled the peaceful image scientists once had. By 2017, as the mission prepared for its final plunge into Saturn's atmosphere, planetary researchers began to realize something extraordinary. Saturn's iconic rings are not ancient, they are young. Using Cassini's measurements of ring mass and the rate at which cosmic dust accumulates on ring particles, scientists now estimate the rings may be only 10 to 400 million years old. In cosmic terms, that is shockingly recent. Even more disturbing, Saturn is already losing them. Charged particles from the rings spiral along invisible magnetic field lines and fall into the planet's atmosphere in a process scientists call ring rain. According to research led by planetary scientist James O'Donoghue at NASA's Goddard Space Flight Center, enough ring material falls into Saturn every 30 minutes to fill an Olympic-sized swimming pool. If those measurements are correct, Saturn's rings could disappear in less than 100 million years. That means we may be living during a brief moment in cosmic history, a narrow window when Saturn still wears the crown that made it famous. But the rings are only the beginning of Saturn's story, because when scientists began looking deeper into the planet itself, they discovered something far stranger. To understand why Saturn became one of the most extreme worlds in the solar system, we have to go back to the beginning, back 4.5 billion years, to the violent birth of a giant. 4.5 billion years ago, Saturn did not exist. There was no ringed planet drifting through the outer solar system, no golden clouds, no shimmering crown of ice. There was only a vast rotating cloud of gas and dust surrounding a newborn star. Astronomers call this structure a protoplanetary disk. It formed shortly after the Sun ignited, when gravity collapsed a giant molecular cloud inside the Milky Way. The event marked the true beginning of our solar system. Inside this spinning disk, microscopic grains of dust began colliding and sticking together. Over time, those grains formed pebbles. Pebbles formed rocks. Rocks merged into enormous bodies hundreds of kilometers wide. Gravity slowly assembled the building blocks of planets, but Saturn formed in a region where the rules were different. Far from the Sun lies a boundary scientists call the frost line. Beyond this distance, temperatures are cold enough for volatile substances like water, methane, and ammonia to freeze into solid ice. That ice dramatically increases the amount of material available to build planets. As a result, planetary cores in this region could grow much larger than those forming closer to the Sun. According to the core accretion theory of planet formation, once a growing world reached roughly 10 times the mass of Earth, its gravity became strong enough to capture enormous quantities of hydrogen and helium from the surrounding disk. When that threshold was crossed, the process accelerated dramatically. Gas rushed inward, flooding the young planet. Saturn rapidly expanded into a giant composed mostly of hydrogen and helium, eventually reaching a mass about 95 times greater than Earth. Yet Saturn's birth was only part of a much larger story. In 2005, planetary scientists Alessandro Morbidelli, Rodney Gomez, Cleomenes Tsiganis, and Harold Levison published a series of landmark papers describing what became known as the Nice model, named after the French city where the research was developed. Their simulations revealed that the giant planets did not always occupy the orbits we see today. Early in solar system history, Jupiter and Saturn drifted into a powerful gravitational relationship called a 2-to-1 orbital resonance. For every 2 orbits Jupiter completed around the Sun, Saturn completed exactly 1. That resonance destabilized the outer solar system. Uranus and Neptune were pushed outward. Billions of icy bodies were scattered across space. Some crashed inward toward the rocky planets, triggering a catastrophic bombardment that scarred the Moon and reshaped the early solar system. Some simulations even suggest the chaos was violent enough to eject an entire giant planet from the solar system forever. Saturn survived that gravitational upheaval, but the violence of its early history may have created one of the most recognizable structures in astronomy. Because the rings of Saturn may not be ancient decorations, they may be the aftermath of destruction. There is a region around Saturn where gravity becomes destructive. Cross into this invisible boundary, and even a solid moon can be pulled apart piece by piece. For centuries, scientists wondered why Saturn alone possessed such a vast and brilliant ring system. The answer began to emerge through a concept first calculated in 1848 by the French astronomer Édouard Roche. Roche studied how tidal forces work near massive planets. His calculations showed that when an object moves too close to a planet, the difference in gravity between its near side and far side becomes extreme. The side closer to the planet is pulled more strongly than the side facing away. If the object crosses a certain distance, its own gravity can no longer hold it together. This boundary is now called the Roche limit. For Saturn, the Roche limit lies roughly 2.5 Saturn radii from the planet's center. Inside this zone, any icy moon that drifts too close will begin to stretch, fracture, and eventually disintegrate. For decades, scientists believed Saturn's rings were simply leftover debris that never formed into a moon. But that idea began to collapse during the Cassini mission. In 2004, the Cassini spacecraft entered orbit around Saturn and started measuring the rings with unprecedented precision. During its final phase in 2017, Cassini performed a series of daring orbits between Saturn and the inner edge of its rings. These measurements allowed scientists to calculate the total mass of the ring system more accurately than ever before. The results surprised researchers. The rings were far lighter than expected, only about 40% the mass of Saturn's small moon Mimas. That discovery forced scientists to reconsider the origin of the rings. In 2023, a research team led by Jacob Kegereis at NASA's Ames Research Center ran hundreds of supercomputer simulations studying collisions between Saturn's moons. Their models showed that if 2 icy moons collided near the Roche limit, the debris could spread into orbit and gradually form the rings we see today. The simulations produced another unsettling detail. Most of the rocky material from the moons would eventually fall into Saturn. What remained in orbit would be mostly water ice, exactly what scientists observe in Saturn's rings. If this model is correct, Saturn's rings are not a peaceful feature of the planet. They are the remains of a catastrophic event, fragments of destroyed worlds slowly orbiting the giant planet. But the story of Saturn's rings becomes even stranger when scientists realize something else. The rings are not permanent, they are disappearing, and the process that is destroying them reveals a deeper interaction between the rings and Saturn itself. That discovery leads directly to the next mystery surrounding the planet. At first glance, Saturn's rings appear stable, almost permanent. Through a telescope, they look like solid bands circling the planet in perfect symmetry. For centuries, astronomers assumed these rings had existed since the birth of the solar system. Modern measurements revealed something very different. The rings are slowly falling into Saturn. This discovery began to take shape during the later years of the Cassini mission. In 2017, as the spacecraft prepared for its final descent into Saturn's atmosphere, NASA scientists directed Cassini through a series of daring orbits between the planet and the inner edge of its rings. These passes allowed instruments to measure the movement of ring particles in the invisible magnetic environment surrounding the planet. What the spacecraft detected was unexpected. Many of the tiny ice particles in Saturn's rings become electrically charged when they are struck by ultraviolet light from the sun or by microscopic dust from space. Once charged, these particles respond to Saturn's powerful magnetic field. Instead of remaining in orbit forever, some of them begin to spiral inward. They slide along magnetic field lines and fall into Saturn's upper atmosphere. Planetary scientist James O'Donoghue and his team at NASA's Goddard Space Flight Center studied this process and gave it a name: ring rain. Their research revealed that enormous amounts of ring material are already being lost. Water from the rings drifts down into Saturn's atmosphere, where it spreads across the planet's middle latitudes like a slow, invisible shower. The numbers are striking. Measurements suggest enough ring material enters Saturn every 30 minutes to fill an Olympic-sized swimming pool. At that rate, the rings cannot last forever. Astronomers now estimate the entire ring system could disappear in less than 100 million years. Compared to Saturn's age of 4.5 billion years, that is an extremely short period of time. This means the rings we see today may represent a brief phase in Saturn's history. Long before humans evolved, Saturn may have looked like an ordinary gas giant with no visible rings. And long after humanity is gone, the rings may vanish again. We may be living during the only era when Saturn appears this way. But the rings are only one part of Saturn's strange behavior. While Cassini was studying the rings, its cameras and instruments also revealed something even more puzzling at the top of the planet. At Saturn's North Pole, the atmosphere forms a massive geometric structure that should not exist in a turbulent gas planet. A shape made not of rock or ice, but of wind. To understand this phenomenon, we have to look at one of the most unusual storms ever discovered in the solar system. In the atmosphere of Saturn, near the planet's North Pole, there is a storm unlike anything seen anywhere else in the solar system. It is not circular like hurricanes on Earth. It is not chaotic like Jupiter's storms. It forms a perfect geometric shape, a hexagon. Each side of this atmospheric structure stretches for nearly 9,000 miles. From corner to corner, the entire formation spans roughly 18,000 miles, large enough for several Earth-sized planets to fit inside its boundaries. And yet this enormous pattern is made entirely of wind. The first hints of this strange structure appeared in 1981, when NASA's Voyager spacecraft flew past Saturn. Images of the North Polar region contained something scientists did not immediately recognize. The data seemed to show a six-sided pattern in the clouds, but the images were limited, and the discovery remained uncertain for years. In 1987, planetary scientist David Godfrey carefully analyzed the Voyager photographs and confirmed the presence of a hexagonal jet stream surrounding Saturn's North Pole. At first, many researchers were skeptical. Planetary atmospheres are turbulent systems. Winds shift constantly, storms form and disappear. A stable geometric structure in such an environment seemed improbable. The mystery remained unresolved until the arrival of the Cassini spacecraft in 2004. Using advanced cameras and infrared instruments, Cassini observed the North Pole for more than a decade. The spacecraft revealed that the hexagon is created by a massive jet stream moving at speeds of nearly 300 miles per hour. Instead of flowing in a circle, the jet stream follows a six-sided path that rotates with the planet itself. Even more surprising, the structure does not drift across the atmosphere. It remains fixed to Saturn's rotation, completing one full turn roughly every 10 hours and 39 minutes. In 2018, researchers led by Lee Fletcher at the University of Leicester published results showing that the hexagon is not limited to the visible cloud tops. Infrared measurements indicated the same hexagonal pattern extends upward more than 300 kilometers into Saturn's atmosphere. This means the storm is not a shallow feature. It is a deep atmospheric structure connected to powerful circulation patterns inside the planet. Despite decades of study, scientists still debate exactly how Saturn's atmosphere maintained such a precise shape for so long. But Saturn's atmosphere has an even more violent side. Roughly once every few decades, the calm bands of clouds explode into a storm so powerful it spreads around the entire planet. To understand how that happens, we have to look at the rare eruptions that transform Saturn's atmosphere into one of the most energetic weather systems in the solar system. Most of the time, Saturn looks calm. Through telescopes, its clouds appear smooth and orderly, arranged in pale golden bands that wrap around the entire planet. Compared with the violent turbulence seen on Jupiter, Saturn's atmosphere once seemed quiet. That calm appearance is misleading. Roughly once every few decades, Saturn releases an enormous atmospheric eruption known as a Great White Spot. These events are among the most powerful storms ever recorded on any planet. The phenomenon was first observed in 1876 by American astronomer Asaph Hall, but for more than a century scientists did not understand what caused it. The storms appeared suddenly, expanded rapidly, and then disappeared again, leaving researchers with only scattered observations. The mystery began to unravel in December 2010. At that time, the Cassini spacecraft was orbiting Saturn, carrying instruments capable of observing the planet in visible light, infrared wavelengths, and radio signals. When a new storm erupted at about 32 degrees north latitude, Cassini recorded the entire event from its beginning. The storm began as a bright white cloud only a few hundred miles across. Within weeks, it expanded dramatically. By early 2011, the disturbance stretched more than 17,000 miles across Saturn's atmosphere. Powerful winds carried the storm eastward until it wrapped completely around the planet. Cassini also detected intense lightning inside the storm using its radio and plasma wave instruments. The flashes occurred more than 10 times per second. Each discharge released energy thousands of times stronger than lightning on Earth. Planetary scientists Chung Lee and Andrew Ingersoll of the California Institute of Technology later analyzed the storm and proposed an explanation in research published in Nature Geoscience in 2015. Deep inside Saturn's atmosphere lies a layer containing water vapor mixed with hydrogen and helium. Over many years, the upper atmosphere slowly cools, forming a stable layer that traps warmer gas below it. Eventually, pressure builds until the barrier collapses. When that happens, warm gas rises violently upward, carrying water ice and ammonia from deep atmospheric layers. The result is a massive convective eruption that spreads across the planet. The process resets the atmosphere, which then begins slowly storing energy again for the next eruption. These storms appear roughly once every Saturn year, about 29.5 Earth years. The last major event occurred in 2010, which means another could emerge sometime within the coming decades. But Saturn's atmosphere is only the outer layer of the story, because orbiting this giant planet are dozens of moons, and one of them possesses rivers, clouds, and seas unlike anything found anywhere else in the solar system. To understand how strange Saturn's system truly is, we now have to travel outward to its largest moon. Nearly 1 billion miles from the Sun, Saturn is surrounded by a vast family of moons. Among them is a world that, at first glance, looks strangely familiar. It has clouds, it has rain, it has rivers and lakes, but nothing on this world contains water. This moon is Titan, Saturn's largest satellite, and one of the most complex environments discovered anywhere in the solar system. For most of the 20th century, Titan remained a mystery. Telescopes showed that the moon was wrapped in a dense orange haze, completely hiding its surface. Scientists knew Titan possessed an atmosphere thicker than Earth's, but no instrument could see through the thick layer of smog surrounding it. That changed in January 2005. As part of the Cassini mission, the European Space Agency sent a small probe called Huygens into Titan's atmosphere. After separating from the Cassini spacecraft, the probe descended for nearly 2.5 hours, transmitting data as it fell through the orange sky. What Huygens revealed surprised planetary scientists. Titan's atmosphere is composed mostly of nitrogen, the same gas that dominates Earth's air. But mixed within that atmosphere is a large amount of methane, a simple hydrocarbon gas. Under Titan's extremely cold temperatures, around minus 180 degrees Celsius, methane behaves very differently than it does on Earth. On Titan, methane acts the way water behaves on our planet. It evaporates from the surface, it forms clouds in the atmosphere, it falls as rain and flows across the landscape through river channels carved into the icy ground. Radar images captured by the Cassini spacecraft later confirmed the existence of enormous methane seas near Titan's poles. The largest of them, Kraken Mare, stretches across an area larger than the Caspian Sea on Earth. This discovery revealed something remarkable. Titan possesses an entire weather system built on methane instead of water. Clouds drift across its skies. Storms occasionally produce rainfall. Liquid hydrocarbons collect in lakes and seas that reshape the surface over time. planetary scientist Ralph Lorenz of Johns Hopkins University has studied Titan for decades and described it as a world where familiar planetary processes operate under completely different chemistry. Yet Titan may hold an even deeper mystery. Some researchers have proposed that Titan's methane lakes could support exotic forms of chemistry that resemble the earliest steps toward life. If that possibility is real, Titan may represent a completely different pathway for biology to emerge in the universe. But Titan is not the most promising place in Saturn's system to search for life. Another much smaller moon is hiding something even more extraordinary. And in 2005, the Cassini spacecraft saw it erupt into space. In 2005, a small icy moon orbiting Saturn suddenly became one of the most important locations in the search for life beyond Earth. The moon is called Enceladus. At only about 500 kilometers across, it is small enough to fit inside many countries on Earth. For decades, scientists believed it was nothing more than a frozen and inactive world. That assumption changed when the Cassini spacecraft flew past Enceladus during its early survey of Saturn's moons. In July 2005, instruments on board Cassini detected something unexpected near the moon's south pole. The spacecraft's magnetometer recorded disturbances in Saturn's magnetic field, suggesting that material was escaping from the surface. When Cassini turned its cameras toward the region, scientists saw towering plumes erupting into space. Jets of water vapor and ice particles were blasting hundreds of kilometers above the surface through deep fractures in the ice. These fractures were later named the Tiger Stripes. The discovery immediately raised a critical question: where was the water coming from? Subsequent flybys of Enceladus provided the answer. Gravity measurements and thermal imaging revealed that beneath the moon's icy crust lies a global ocean of liquid water. This ocean is buried beneath roughly 20 to 25 kilometers of ice, but in the south polar region the ice shell becomes much thinner, allowing water from the interior to escape through the cracks. Cassini flew directly through the plumes multiple times, allowing its instruments to sample the material coming from the ocean. The results were remarkable. The spacecraft detected water vapor, salt-rich ice grains, organic molecules, and molecular hydrogen within the plumes. In 2017, a research team led by Hunter Waite of the Southwest Research Institute published their analysis in the journal Science, concluding that the hydrogen most likely comes from hydrothermal reactions occurring on the ocean floor. On Earth, similar reactions occur near hydrothermal vents deep beneath the ocean. These environments support entire ecosystems of microorganisms that survive without sunlight, using chemical energy from the interaction between water and rock. This means Enceladus possesses three of the key ingredients scientists believe are necessary for life: liquid water, chemical energy, and organic molecules. Even more remarkable, the ocean is continuously spraying material into space. Instead of drilling through kilometers of ice to reach the ocean, a spacecraft can simply fly through the plume and analyze the particles directly. For planetary scientists, Enceladus has become one of the most promising places in the solar system to search for extraterrestrial life. But Enceladus also reveals something deeper about Saturn itself. Because the activity of this tiny moon is powered by the enormous gravitational forces of the giant planet it orbits. To understand the source of that energy, we must finally look beneath Saturn's clouds and into the extreme environment hidden inside the planet. If you could fall towards Saturn, there would be no moment when you hit the ground. The clouds would grow thicker, the light would slowly fade, pressure would rise continuously as the atmosphere deepens into something far more extreme than ordinary gas. Saturn is not a planet with a solid surface. It is a world where matter gradually transforms under immense pressure. Understanding this hidden interior became one of the major goals of the Cassini mission. Between 2004 and 2017, Cassini performed detailed measurements of Saturn's gravity field and magnetic environment. By studying subtle variations in those signals, planetary scientists were able to reconstruct the internal structure of the planet without ever entering it. One of the most surprising discoveries emerged in 2019 when researchers Christopher Mankiewicz and Jim Fuller at the California Institute of Technology analyzed patterns inside Saturn's rings. The rings act like a giant seismograph, responding to vibrations produced by the planet itself. By studying these patterns, scientists could indirectly observe motions occurring deep inside Saturn. Their results suggested that Saturn does not contain a simple solid core surrounded by gas. Instead, the interior appears to contain what scientists now call a fuzzy core. Rather than forming a compact ball at the center, heavy elements such as rock and ice appear to be spread through a large region extending across nearly 60% of the planet's radius. This mixture gradually blends into the surrounding layers of hydrogen and helium. Deeper still, the conditions become far more extreme. At pressures reaching around 2 million times the pressure at Earth's surface, hydrogen undergoes a dramatic transformation. The atoms are forced so close together that the gas behaves like an electrically conducting liquid metal. This layer of metallic hydrogen is believed to generate Saturn's magnetic field. As the liquid metal slowly circulates inside the planet, electrical currents form, creating the vast magnetic bubble that surrounds Saturn and influences the motion of charged particles in its rings and atmosphere. Yet Saturn's interior holds another mystery. Observations suggest that helium inside the planet may separate from hydrogen and form droplets that fall deeper toward the core. This phenomenon, known as helium rain, releases additional heat as the droplets sink. That process may explain why Saturn radiates more energy into space than it receives from the Sun. The deeper scientists look into Saturn, the less familiar the planet becomes. But the final surprise hidden inside this giant world may be the strangest of all. Deep in Saturn's atmosphere, carbon may be transformed into something unexpected, and under the immense pressure of the planet's interior, that carbon may fall through the darkness in a form no one would expect. Deep inside Saturn, far below the clouds and violent storms, the planet enters a region where chemistry behaves in unfamiliar ways. Temperatures climb into thousands of degrees, and pressure becomes so intense that common materials are forced into entirely new forms. One of the most surprising consequences of this environment may be something that sounds almost impossible. Diamond rain. The idea begins with methane, a molecule made of one carbon atom and 4 hydrogen atoms. Methane exists in small quantities within Saturn's upper atmosphere. Under normal conditions, methane is stable, but Saturn's atmosphere is filled with powerful lightning storms capable of breaking these molecules apart. When lightning strikes, methane can separate into hydrogen and free carbon atoms. Those carbon atoms do not remain suspended for long. Gravity slowly pulls them deeper into the planet. As they descend, pressure increases dramatically. Laboratory experiments performed in 2017 at the SLE National Accelerator Laboratory recreated similar conditions using extremely powerful lasers. The experiments showed that carbon exposed to pressures like those found inside giant planets can compress into solid diamond structures. Planetary scientists now believe this process may occur naturally inside Saturn and Jupiter. In this scenario, tiny carbon particles first form soot-like grains in the atmosphere. As they sink deeper into the planet, pressure squeezes those grains into graphite. Deeper still, the graphite transforms into diamond. These diamonds would not be gemstones like those on Earth. They would form in complete darkness inside a dense ocean of hydrogen and helium, slowly falling through the interior of the planet. Some models suggest the diamonds could eventually melt in the intense heat near Saturn's deep interior, forming a strange layer of liquid carbon surrounding the planet's core. This possibility illustrates how extreme the environment inside Saturn truly is. The planet that appears calm and elegant through a telescope hides processes far beyond ordinary experience. Metallic hydrogen flows like liquid metal. Helium may fall as rain. Carbon may crystallize into diamonds before sinking into darkness. Saturn is not simply a giant sphere of gas. It is a dynamic system where gravity, pressure, and chemistry constantly reshape matter itself. When scientists first observed Saturn centuries ago, they saw only a distant ringed planet. Today we understand it very differently. A world of collapsing rings, planet-wide storms, alien oceans on its moons, and extreme physics hidden deep within its interior. And yet Saturn is only one example of a type of planet that appears throughout our galaxy. The same processes unfolding inside this giant world may be happening on countless other planets orbiting distant stars, which means Saturn is not just a beautiful object in our solar system, it is a glimpse into how strange giant planets across the universe may truly be.